Hello, today we're going to talk about atomic bonding structure. Alright, the first thing we're going to talk about is periodic trends. So all bonding involves chemical changes. The changes take place in the valence energy shell, which is the outermost shell. So if we talk about family trends, so families are the vertical sections of this. So, as you can see, I've written out for family 1. So this is family 1 trends. Alright, so we have hydrogen first, and it only has 1 electron on the outside in its valence or its most outer energy shell. Then we go to lithium. Adds a shell, but it still has how many electrons on its valence? Energy level, 1. Then we come over here to sodium, adds another shell. So this had 1 shell, 2 shell, 3 shells. And now it still has 1 electron on the outside. Here we go to potassium. It has 1, 2, 3, 4 shells, but it still has how many electrons on the outside? 1. So what this tells you is, as the family goes down, so we have hydrogen, then lithium, then sodium, and then potassium. As you go down, you increase shells by 1, but you still have the same amount of electrons on the outer shell. So in family 1, I have 1 electron on the outside. What if I went to family 2? Well, if I went to family 2, they would still increase shells as they go down. But how many electrons do you think would be on the outside in the valence thing? 2. All right, now you hop over here to the other side. Alright, and you have 13, 14, 15, 16, 17, and 18. It's not very to scale, but it's fine. So if I have 1 here and I have 2 here, and these are what are called your main group elements. So 1 and 2, and then 13 through 18 are main group elements. And this is the only thing these apply to, this outer elements. This trend that we're seeing with the increased shells by 1 and 1. So this has 1 electron on the outside. This right here, this family has 2. So now we come over to 13. This has 3 in its outside, then 4, 5, 6, 7, and 8. All right? So these are called noble gases, and they have the perfect octet on the outside. All right, so that's the trend here. So increase shells by 1 as they go down, but as they go from left to right, they increase the electron in the valence shell by 1. So this will always have 1, 2, 3 electrons, 4 electrons, 5 electrons, 6 electrons, 7, and 8 electrons in their valence energy level. All right, I'm going to show you that last part that I just told you. So as I said, as they go down, I showed you they increase the shell each time. As you go left to right. So we have sodium already up here, so we use that. So then I have magnesium next. As you're going over, it has 1, 2, 3 shells, because it's 3 down, 2 here, 6, 7, 8. But this had 1, so this has 2 on the outside, which makes it element 12. Or atomic number 12, or 12 protons, whatever you want to call it. Then I move all the way across the board, and I go to aluminum. Oops. Let me do aluminum here. So, still 3 shells, 2 here, 8 electrons in the second shell. But I went from 1 to 2, now I have 3. And this will continue all the way over. If I did, what's that, silicon? If I did silicon, 1, 2, 3 shells, 2 here, 1, 2, 3, 4, 5, 6, 8 here, and then 1, 2, 4 electrons in its outer. And that just keeps going all the way over to the right. So based on its family, as you go down, increase shells by 1. As you go over to the right, as you're looking at it, so to the right, you increase the number of electrons in the valence energy level. All right, so now we're going to talk about noble gas. Noble gas is over here at 18. It has a perfect octet on the outside, which means it doesn't bond, right? Helium is up here too, but helium doesn't have an octet. It only has the 1 shell that holds 2 electrons, but it still has a complete shell, so it's over there. Hydrogen, way over here, doesn't need a complete octet to bond because it has 1 electron in its middle shell, or in its first shell, which can only hold 2. So it actually only needs 1 electron to become complete. So it is hydrogen has 1 shell, 1 electron, doesn't need octet. Helium has 1 shell, 2 electrons, but it has a full valence shell, even though it doesn't have 8 electrons. So all the noble gases have an octet and the valence energy level. All right, now ionic bonding. We've talked about this in previous videos. To have an ionic bond, you have to create ions. What an ion is, so let's take sodium here. So what happens for sodium to become an ion is it doesn't take much energy to pull an electron or 2 from the outer shell. These are called active metals, because the next shell will be an octet. So it really wants to bond because it only has 1 on the outside. It doesn't take much energy to take 1 or 2. When you get to 3, it becomes a little bit more difficult. So these metals over here like to bond a lot. So for this to become an ion, all that happens is this electron leaves, and now it has a perfect octet on the outside, but it's positive because it lost an electron. When an ion loses an electron, it becomes positive. When it gains an electron, it becomes negative because electrons are negative. So families 1 and 17 like to bond a lot because this has 7, this has 1 electron in its valence energy shell. So together they make 8. 1 also will bond with 16, which is why you have H2O, which is water, because you have 2 hydrogens, so that gives you your 2 that you need, 2 electrons, to bond with 1 oxygen, which is 6, to get H2O. So these will bond well with, the best with 17, but they'll also bond with 16, but you'll need 2 of them. And 2 likes to bond with group 16. All right, now I'm just gonna read. So covalent bondings, and when energy requirements are too high to transfer electrons, they share. So when you get over here in your non-metal sections, like 4 and 5, when you're trying to bond them, it's easier just to share than to pull like 4 electrons away from something. All right, so they just share, and that's covalent bonding. There's a video on that if you want to go back and look at it. So in a covalent bond, they don't transfer, they just share because it takes so much energy for them to take it out of the energy level. Then we have exothermic and endothermic reaction. So an exothermic reaction is releasing energy to become self-sustaining. So like wood burning, wood won't burn, just catch on fire and start burning. What it needs is an initial light, but once wood starts burning, it starts a chemical reaction inside of it to keep it burning. You don't just light the wood, catch it on fire, then it stops as soon as you're done. No, you set wood on fire, and that creates energy that happens inside to a combustion reaction inside to keep it lit and turn into ash. Endothermic reaction requires constant input from outside source like photosynthesis. Plants are continually getting energy from the sun. There's your endothermic reaction. So exothermic is from inside, endothermic is from outside. The last part is indications of a chemical change. So a new substance being made, basically like wood burning to ash. So when wood burns, it becomes ash. It doesn't have the same chemical properties anymore. So some signs are a precipitate is formed, bubbles, color change, something gets hot, and when you see the production of heat and light, it's an indication of forming bonds, chemical change, and breaking bonds. All right, this has been atomic bonding structure. Hope it helped.